Hello everyone and welcome to this section. In this section, we're going to learn how to build one single neuron or a single, what we call it, perceptron model, okay? All right, so let's get started. So this is a kind of an image of a single neuron, okay, within our human brain. As we mentioned earlier, in general, our human brain works in a way that we have kind of a nucleus in here, and what we do is that we acquire different signals from, we call it different dendrites, okay? We send all these signals into a neuron, and that neuron kind of a nucleus, and within that nucleus, some processing happens in a way. I'm gonna show you how can we model that mathematically. And then afterwards, we send the output into what we call the axon here, which is the output that we send to the next neuron and so on, okay? All right. And what will happen is we have hundreds of billions of neurons connecting to each other, talking and communicating to each other, and that's kind of the miracle of the human brain. And when we learn, when we say that we were able to learn, that's when we actually change the strength of the connection between these neurons in a way. Okay. All right. So let's model that mathematically. And once we model that mathematically, just one neuron, we can build kind of our own mini brain in a way. Okay. So let's get started. So what happened is, again, as we mentioned, we have a couple of dendrites. These are kind of, that's inputs here. We have our nucleus, the processing happens inside, and we have our axon, that's the output, okay? So when we do that mathematically, okay, we'll say, assume, okay, we have all these inputs going into, which is the dendrites. We're gonna assume there are a bunch of inputs. We're gonna call them, let's say, x1, x2, x3, okay? Here, we have a neuron. I'm gonna show what we can include, mathematically within that neuron. And here, the values connecting, for example, the input x1 to the neuron, we're going to assume it's kind of weights, okay? All these are simply numbers, okay? You can put here weight, for example, like 0, which means any input we're going to be inserted here, we multiply it by 0 and then send to the nucleus or the neuron. x2, we can multiply it, let's say, by weight 2 of 1, which means you're going to pass it on. And then you can change, for example, the values of the weight. You can increase the strength of the weight by making it, let's say, W310, which means whatever input we're going to be sent here to X3, we actually multiply by value of 10, for example, and so on. And that's how you change the importance, for example, of these different inputs or of these different neurons in the previous layer, okay? That's pretty much how can we model it, again, in a very, very simple form, all right? So let's take a little bit of more kind of look into the mathematics of it. Okay, so here we have again our neural model. Here we have what we call it the inputs, which is x1, x2, x3. And all these inputs are, we call it independent variables, okay? The objective here of building this neuron or artificial neural network is that I have a bunch of inputs or a couple of inputs, which is x1, for example, inputs. I have y outputs, and I want this neuron or this like artificial neural network to learn the pattern, okay? To learn you in a supervised fashion. When you see these inputs, we're gonna generate that output, okay? And that output can actually be binary, can be, let's say, 0 or 1, which means, you detected, for example, a pedestrian or not. Okay, so if it's not a pedestrian, that means the output will gonna be 0. If there is a pedestrian, that means the output will be 1. And that's why we call it a binary classification, okay? Or it might be categorical classification, which means, for example, in our traffic sign classification problem, we're going to classify traffic sign to, let's say, 1 out of 43 traffic signs. 30 kilometers an hour, 60 kilometers an hour, 100 kilometers an hour. There is yield, there is pedestrian, there is no entry, and so on and so forth, okay? And that's what we call categorical. We have different categories, and here the output, we can have various outputs where each of these signals identify a category, okay? And then the last one is what we call the continuous signal. We can actually use, for example, artificial neural network to perform regression, for example. So we can have the output not as a binary, not as a categorical. We can actually use it as a continuous signal, okay? All right. So again, that's pretty much how can we model a neuron mathematically. And if you guys can see here, the weights can be used to show the strength of a particular node. So here, we can change the value of the weights, and that's how we indicate how the neuron, preceding neuron actually has kind of an importance to it. Okay, all right. So let's open that neuron and see what's inside there. Okay, mathematically. All right. Okay, so let's get started. So what we're gonna do is that we assume that this neuron, okay, which is the mathematical neuron that we kind of developed, has a kind of a summation okay, along with what we call it activation function, okay? Again, I promise you not to go in like in depth through a lot of math, because there's a lot of math involved. I'll try to make it as practical as possible, and then we're gonna learn how can we actually model that and develop like kind of in Python, actual code for it. Okay, but I want you guys to understand the intuition. This is very important. You can't just go and build an artificial neural network without knowing the intuition, what's happening from a very high conceptual level. Okay, so what happened here, again, I have my inputs, I have my output y, okay, and each of these inputs are gonna multiply by weights. So simply I'm gonna multiply x1 by w1, and then I'm gonna multiply x2 by w2, x3 by w3, and I'm gonna do is we're gonna basically sum them up. Okay, and that's how you can see the summation here. And then I'm gonna use what we call it a bias signal, okay? Bias can simply be used to change the level of the function, okay? In like the summation in total, okay? You can set the bias to 0, for example, but in general, bias will be one of the tunable parameters as well, okay? Or a number of adjustable, what we call it adjustable parameter as well, okay? And then the outcome, the output from here, we can apply a kind of an activation function to it, okay? The activation function can be lots of things. I'm gonna have an entire lecture to actually talk about different activation functions we're gonna be using in our network, okay? All right, so the key element or the key question here, and that's what part of the questions we're gonna go through during the coding exercise. How many adjustable parameters do we have in one single neuron model like this? Okay, so first of all, if we have 3 inputs, that means we have 3 weights, okay? And we have a bias signal too. So we have 3 weights plus 1 bias, that means we have 4 adjustable parameters, okay? All right, that's great. What if we have 2, for example? Again, all these we're gonna show them when we go through building 2 neuron models and multiple or multi-neuron models, okay? All right. Okay, what about the activation function? Let's take a look at a kind of a practical example, okay, that have actual real numbers along with an actual activation function. Let's assume that we have an activation function that we call it unit step, we'll call it threshold activation function. Simply put, if my input is simply smaller than 0, okay, if x is smaller than 0, we're gonna set the output to 0, okay? If my input x is greater than 0, we're gonna set the output to 1, all right? It's kind of a binary values. Whenever I'm below, if the input is negative, we're gonna set it to 0, okay? If the input is positive, we're gonna cap it to 1 in a very simple form, okay? All right, and that's our network. We have a bunch of inputs. We have x1, x2, x3. We have, again, our summation. We have our activation function. Let's assume that these inputs are, let's say, value of 1, 3, and 4, okay? So let's go through what we call it forward run within the network. We have our input, and let's see what's gonna happen, you know, from a mathematical point of view until we actually go through the different layers and generate the output, okay? So our input 1 will be multiplied by the weight, which is 0.7, okay? That's the first step, and that's 1 times 0.7. And then we have input number 2, which is the value of the input, x2 is actually 3 here. 3 times 0.1, which is 3 times 0.1, that's the second input. We have 4 times 0.3, that's my third input. And then afterwards, we're gonna apply the bias. Here I'm assuming the bias is 0, that's why I ignore the bias per se. And then afterwards, all that signal, again, I didn't apply the activation function yet. This value here is 2.2, okay? And then I'm gonna apply the activation function. Since the activation function here in this case is actually the input, which is to the activation function is 2.2, that means it's more than 0, that means we're gonna set it to 1. That's why the output is equal to 1 in a very simple form. That's how we actually model one single neuron using a unit step activation function, okay? All right. So let's take a look at kind of a fun simulations that we can use, do using what we call the playground for TensorFlow. All right, that will show you how can we build different neurons, for example, and so on. Let's go there and let's get started. All right. So this is kind of, you know, like we call it playground to build your own mini brain per se. Again, there's no data, or there's no like we're not actually like modeling anything in Python, for example. This is kind of a playground for you. Okay, so here we have what we call it our own features. These are kind of the inputs that we have. In our case here we have x1 and x2, which is just 2 inputs, for example. We can actually increase it to make it, let's say, 3 inputs or whatever. And then here we can actually build kind of our own neurons. So if we want to have just one neuron model, we can just build our one neuron model. And then here we can add different hidden layers, for example, if we want to. So that's if you want to add, for example, additional neurons. If you want to add additional neurons, that's how you can build kind of your own artificial neural network per se, okay? Here you can change your activation functions. Again, I haven't went through the activation functions yet, but that's again the list of all activation functions. I'm going to show you what do you mean by all of this. We're going to show you again moving forward how we do like regularization per se, and how do we change that rate, and then how can we change the learning rate as well. Okay, so let's take a look at a very quick, simple example. We're going to assume that we have all our neurons, or let's say, you know, like we're going to remove even this. We're going to remove one hidden layer, and that's our very simple model to just have 2 inputs with 1 neuron, and that's what we call it, one neuron model that we actually built already kind of from a mathematical perspective. Okay, we can change this, for example, make it linear, so the outputs actually here through the activation function is pretty much linear, and we can use it just to classify 2 samples. All right, so let's get started and let's train it. Again, this is just kind of an overview to show you how can we build, you know, kind of network quickly. And moving forward, they're going to show you how to do actual classification, how to actually perform training, and how we build a multi-layer perceptron network. If you just click play, that's you're going to see, okay, that's how learning happens or learning occurs. And you can see that we actually built kind of that classification border or line between these 2 classes. That means, okay, we classified, for example, the input to whatever one of these 2 classes. Okay, all right. What if you want to change, for example, the number of neurons? You can change number of neurons. You can click play. I'm going to show you again, because it's very simple example, just linear classification. However, if you want to make it a little bit more complex, if you again, you're going to run it, we're going to show you that we know like the network in this fashion can classify something like this, because, you know, because the model is very simple. We only have 5 neurons. We need more hidden layers. We need, for example, more neurons and so on. Let's add, for example, one additional hidden layer. Let's, you know, add neurons, and let's give it a shot. You will see again, we're trying to train. It's trying so hard to find that boundary between the 2. Okay, but again, it's pretty difficult. Okay, maybe let's change the activation function. Let's make it, for example, ReLU activation function. I'm going to show you what they mean by ReLU or rectified linear units. It's actually fascinating. So when you actually add the ReLU function with two hidden layers, each of 6 neurons, was very easy to actually draw that boundary. Okay, and that's pretty much what we're gonna show you throughout the entire section. How can we build our artificial neural networks? How can we change our activation functions to actually do different classification problems, as you guys can see here. All right, and that's pretty much all what I have for this section. I hope you guys enjoyed it, and see you in the next section.